Our today's presenters are Marcos Cordeiro and Befecato Walder-Georges from the Faculty of Agricultural and Food Sciences at the University of Manitoba. And they will talk about running parallel jobs in HPC environments based on their own experience, from setting up the workflow to post-processing job output. Without further ado, I will pass the microphone to Marcos and Befecato.
Great. Thanks, Alex. Can everyone hear me okay? It's a thumbs up. Okay, great.
Yep.
So thanks, Alex. Thanks for the opportunity to present. And my name is Marcos Cordeiro. I'm an assistant professor in the Department of Animal Science at the University of Manitoba, as Alex just said. And my research program is on agroecosystems modeling. So we do large-scale modeling, we use all sorts of tools. And HPC has always been something that's it's important for our program, but it's becoming more and more central as we start to expand the scale of our modeling exercises. So when we were discussing this presentation, I had three things in mind, right? So one of them, two of them are in the title, the third is not. One of them is we try to gear this to new users, right? So this presentation and the title was crafted to hopefully attract people from non-traditional fields like agriculture. This is what we do in other fields as well, because it's sometimes hard to break that barrier. So we'd like to, invite people in to learn a little bit more about HPC systems and their use in research that's non-traditional fields. The second point was to real case application. As you see from Befecato's presentation, there's a few aspects there that may seem relatively complex and advanced. And we decided to keep those aspects there because we didn't want to water down the example too much. So you see how HPC can be used, but also you see how HPC can have some complexities. And the idea for us was to give some tips and tricks on how to navigate those complexities. And the third point that we tried to incorporate here was a live demonstration, because these are great learning tools, right? Nothing like you see, an example being worked out. So this is what Befecato prepared. I know, people who take my lectures, they know I love live examples, even though we open the door for things that can be wrong, especially with computers and things like this, connections. But we decided to take the risk and try to do that demonstration. So Befecato will walk you through the presentation, then walk you through an example. That's a real application, just scaled down. So in order to save, I think this is all I wanted to say. I want to open the floor for Befecato. He will take over from now, and I'll join you at the end of the presentation for questions. Okay, thank you, Befecato. Please go ahead.
Thank you, Alex and Marcos, for the nice introduction. My name, as they introduced, is Befecato, and today I'm going to talk about essentials of high-performance computing from new users' perspective, using hydrological example. So my talk is going to have three parts. In the first part, I'm going to talk about the importance of HPC. And then in the second part, I'll present a typical workflow I use to submit a hydrological modeling job to an HPC. And then in the third part, I will present demonstration of some important aspects that I will cover in the workflow. So from hydrological modeling perspective, usually we go through a series of steps when we do a modeling exercise, starting from wanting to know which parameters are quite essential with regard to influencing the model behavior, and then calibrating our model. And lastly, we might want to do uncertainty quantification. Taking an example of a sensitivity analysis, if we might want to run a global sensitivity analysis using a model with 40 parameters and number of simulations required around 84,000 for the sensitivity analysis to converge. And if we assume that a single simulation takes a minute, we would require around 60 days for the job to be completed if we are going to run sequentially. And this is quite impractical for most applications, unless we have some sort of parallel computation. The problem with using parallel computation is usually it's memory intensive and might require several CPUs depending on the nature of the job. So this might not be handy to accomplish on local computers. HPCs can be quite attractive in this sense. If we take an example of the CIDR cluster on Digital Research Alliance, we can have access to 48 parallel cores per single node, and we can submit a job to run for 28 days. On top of that, we can submit multiple jobs depending on resource availability, and this can give us a huge capacity to accomplish an enormous job in a short period of time. Coming to the workflow that I typically use to run a job, as a beginner, the first step might be to get registered and have an account on the HPC. For that, you can go to the Digital Research Alliance and click on the register button and follow the steps. Once you have an account, you might want to know more about the cluster regarding the software availability, the space that you can use. For instance, there are 3 spaces on the Digital Research Alliance: the home space, you have the project space, and the scratch space. Typically, I use the scratch space because it gives me ample room to deal with massive input-output files and to run parallel computations. On the other hand, you cannot submit a job from the home space. You have to have information regarding such type of critical aspects before you use the HPC. And as a beginner, even after having some experience, I strongly recommend to develop your code on your own computer and make sure that everything runs smoothly at a scaled down version before you move to the HPC, because there might be much more uncertainties if you are not used to that environment. Then it's important to make a secure connection to the HPC and be able to transfer files. Once you have all the files transferred, you can test your job, and then you can submit your job. Once you submit your job, you might want to know the status, whether it's running or pending. So you should be able to monitor the job and retrieve your results, maybe after some post-processing. Regarding transferring a file, there are different methods. The first of which could be using SSH file transfer protocol, such as WinSCP and FileZilla. Particularly, I use WinSCP because it's so much easy to use on Windows. It's particularly designed for Windows operating system. So if you use WinSCP, you install it on your computer, you launch it. This is the type of screen you get, and you have to enter the username, the host name, your password. For instance, if I want to get a secure connection to CDAR, I can enter cdar.computecanada.ca. Recently, I have learned that there has been a new development regarding the host name, whereby Alliance CAN is substituted for Compute Canada. Maybe as a first-time user, you might want to adapt that. And then once you enter all these details, you can click login, and you have a secure access to initiate file transfer. So in this window, the file system on the left-hand side is the one on your computer, and the one on the right-hand side is regarding the files on the HPC. If you don't have folders that are ready to transfer files to, you can create one just by right-clicking and creating directory, and then you can select from the left-hand side window as many folders and files as you would like to transfer to the HPC, and then drag and drop into a specific path of your interest on the HPC. Alternatively, you can use a command prompt or a PowerShell by using the SCP command. If you are transferring a folder, you might want to use the arrow option to transfer files recursively, and then you provide the path of the file on your computer. Then you provide a space, and then your username at the host name, which is cdar.computecanada.ca in my specific example, followed by colon, and then the destination on the HPC. Then it can do the job for you. It can transfer the files. Once you transfer your file, you would like to get access to the HPC in order to do certain operations. For that, I use PADI. You can use an SSH client like PADI. So you install that application. If you are a Windows user, you might not want to use this if you are already using Mac or other operating systems. And then you have to provide the host name and click open. You'll be prompted to enter your username and then your password. And then you get access to the command line interface. So from this point, you can start changing your path to the working directory where you would like to run your model, or you can start searching for software availability. Usually I use R. So if I would like to know which version of R is installed on the HPC, I can use the module spider command and then provide R / the version of the R. If I don't know that, I can keep just this keyword and press enter. I'll get the list of software with this keyword. Then I can scroll up and down until I locate the different versions of R that have been described. Then once I know the versions available, then I can pick the one I'm interested in or the one I have been working with. And then I can load that particular software. So if I would like to work with this version of R, I can just use module load and then the name of the software or the module. Then the module is loaded. I can install packages. Typically, when you are working with R, only a few packages come with the base version of R, so you have to install different packages for your own operation. If, for instance, you would like to install a sensitivity package, first you have to download a compressed version of the package, and then you have to provide the path to that compressed file as an argument in this command. And then once you turn dependency to true, it can take care of installing the package along with all its dependencies. The reason why we usually use high-level programming languages is the fact that it makes life easy concerning pre-processing, post-processing, calling applications, and so on. So for instance, if you are running a hydrological modeling job, you might want to edit your parameter file before you start running the application. So you can do that very easily using R or Python. I particularly use R. Then after I make change to my parameter file, I can call the application using the system command in brackets and quotation mark. If I provide the name of the executable, and if I'm in the right directory, it actually launches the application. On top of that, there are various packages that are available. So we can use those packages for particular purposes of our interest. For instance, for sensitivity analysis, optimization, parallelization, data manipulation, and so on. We can also use these types of high-level programming languages to post-process our results. Now we have loaded the software of our interest. We might want to compile a source code, particularly if we have been working on Windows operating system. The fact that the HPC works with Linux operating system, we have to compile our source code on the HPC in order to be able to have an executable compatible with the new operating system. So for that, we have to load the appropriate compiler, and then we can use the make command. And usually make files are made available with the source code, so we can easily compile our source code and have the application to run. If you have the objective of running parallel computations, there are certain aspects that you have to keep in mind. You are going to run multiple copies of your model, and you have to update your parameter files. You have to write an output to the output file. So you cannot do this for multiple tasks in the same folder. So you might want to create subfolders in order to be able to run the jobs without interfering with each other or without overwriting your output files or parameter files. And together with this, you might want to create symbolic links, especially if you are dealing with large-scale applications involving massive input files. You might not want to copy all those files into individual subfolders. Instead, you can create a soft link in the subfolder such that it points to the original file in the root directory. So you can automate the process of generating the symbolic link along with creating the subfolders using a shell script. This is a typical shell script I use to create subdirectories. For instance, here I'm running from 1 to 16 and creating subdirectories with this naming pattern. So n is changing from 1 to 16. I would like to draw your attention to this specific line where I'm creating a symbolic link. So this is a subfolder that it's creating automatically. So I'm creating a symbolic link for this file in this particular subfolder, pointing to the root directory with the same file name. So you can generate as many symbolic links as you want, depending on the number of files you would like to have a symbolic link for. If you don't want to create a symbolic link and instead you would like to copy certain file, you can just use the cp command instead of the ln with the sf option, and you can make it recursive with the R option if you are copying folders, but for a single file, you might not want to use this. Then your shell script must be made executable in order for you to be able to run it. So you can use the shmod plus X command and provide the name of the shell script, then it becomes executable, and then you can use the // command and then the name of the shell script in order to run this shell script and create the subfolders and the symbolic links. The other aspect that you must be aware of is the fact that you are running multiple copies of your application in separate subfolders. You have to make sure that the right change of directory is being made whenever those processes are concurrently being called. So for that, I typically create a batch file whereby I automate the name with the index of the process being part of the file name, so that inside each of these batch files, though my batch file is going to be 16, for instance, if I am going to have 16 parallel processes. So inside this batch file, I have a list of parameters that needs to be passed, and then I have to make change to the right path. For instance, if this is ID1, so it's corresponding to process 1, my subfolder suffix is going to be 1. That's how I named my subfolders. And then it's important that here I have for me to mention that I'm running two applications, one parameter editor and the other one, the model itself, sequentially. So I want to make sure that these processes do not interfere. So I get the process identification ID of the parameter editing process, and then tell the shell to wait until this process is completed, and then launch the model itself so that I make sure that it doesn't start running before the parameter editing is finished. And once I'm to this step, it seems that everything seems ready. So I have to test my job, whether it's going to run smoothly before submitting, because usually you might have your job set in the queue for resource allocation purposes. That's what the scheduler does usually. So you might want to not have an error after waiting for a couple of days. So it's important to test your job to make sure it runs smoothly. And I use the sallow command to get a temporary access to a scaled down version of the computational resources and make sure it runs smoothly. I'll come back to this command in the demonstration. So be prepared to get an error. Typically, as a beginner, and even after you have a decent experience with parallel computation, you might get an error. And the type of error that you usually get is very crude and doesn't tell you where it's originating from. So I would like to mention the fact that when I create a cluster, I use the parallel library with the make cluster command. So I'm only providing the number of cores as an argument. And then I initiate the parallel computing using the for each command and do par. Here I can add more arguments, especially if I would like to have more information regarding the error or where it's originating from. I can add this more argument out file. And then when I run, more detailed information regarding the origin of the error can be printed. So here it's telling me where the error is originating from. It cannot find this file name. Actually, I introduced this error intentionally for demonstration purpose. And once you, if you are able to trace back the origin of the error, it's fine. If it doesn't work, alternatively, you can serialize your job by commenting the line where you initiated the parallel processing. You can manually provide the ID for which you would like to run the process. You get that ID where the error message was thrown. And then you can run the job, and you might use printing debugging approach or whatever works for you to accurately determine where the error is originating from. Once you fix your error, the next step is to submit the job to the HPC. So you have to create a submission script whereby you define certain parameters regarding environment variable, the resource that you are requesting for, and the specific script that you would like to launch. So the submission script basically initiates the scripts that I'm using R. Actually, it initiates the R scripts to run, whereby the R script calls the hydrological model along with the parameter editor and writes the output file as intended. So this is a typical submission script that I create. I start by providing the path to the bash shell program. That's a kind of environment variable. And then I define the parameters of the computation using the sbatch command preceded by pound symbol. So I have to define the number of nodes, the tasks per node, the memory I require to complete the job, the time for the maximum time for which the job is supposed to run, and then the job name. If you are running or submitting multiple jobs at a time, you might want to have a unique job for each of name for each of them to distinguish. And then you have to provide the account you are using. I'm using more than one account with the Digital Research Alliance of Canada, so I have to provide which account I'm using. And important here is, since I'm going to use R to do the job, I have to load the appropriate version of R in the submission script. So if I don't do this and I call R, it doesn't recognize. So I use the module load command along with the version of the R, and then I can initiate running the R script using the rcmd bash command. That's what I usually use. You can alternatively use the R script command as well, but this is the one I use. And once I prepare my job submission script, I can use the sbatch command, space, and then provide the name of the submission job script that I have created, press enter, and the job will be submitted. Once the job is submitted, I might want to know its status. It might not start right away. So I would like to check whether it's pending or if there is anything wrong. So I can use the sq command -u and then your username to get the list of all the jobs that you have submitted, and either they are pending or they are running. Those that have failed, you won't see by using this command actually. And then if I'm interested in a particular job, to see more details, I can use the s-control show job and then provide the job ID, which I get from the sq command. This gives me more information regarding when the job is going to start, the command that was used to submit the job, the working directory, and so on. Now I would like to take you to the demonstration part. So I would like to start by, let's say, let me open a new WinSCP. Remember, I was telling you an SSH file transfer protocol you can use to securely make connection to the HPC and transfer files. So as a new user, these are the names I usually use to get access to different accounts that I have on the Digital Research Alliance. As a new user, you will use this one, and then you have to provide the host name. Since I would like to get access to the CDAR computescanada.ca, that's the host name, and then I have to provide my username along with the password that I have created, and then click login. Now it's making a secure connection to the HPC. So as I was explaining in one of the slides, on the left-hand side are the file system on my local computer, and on the right-hand side shows me the file system on the HPC. I was talking about the scratch space, so I can double-click this to get access to the scratch space. As a new time user, you won't have any file here or folder. So you have to right click, create new directory, and you can give whatever name you are interested in, and then you can click OK. It will create a new folder. Then you can select the files that you would like to transfer to that path that you just created, or you can navigate. For instance, if you would like to change this path, you might want to go back and make change of directory. For instance, if I would like to make transfer of files from a specific folder along this list, I can select which one I would like to transfer and drag and drop into the destination of my interest on the HPC. So this is how I securely transfer file. The next step is I would like to get access to the HPC and be able to do certain operations. So as a new time user, you don't have any saved sessions. So you have to provide the host name, cedar.compute-canada. This can be different depending on the account you have, and then click login as. You provide your username, and then you'll be prompted to enter the password. So this is a command line interface that I can use to do certain operations. I might want to start by making a change of directory to the specific path where I would like to work. So I can copy this path. This is where I'm going to do the live demonstration. So I can make change of path to this particular path. Strange. It was supposed to change here. Okay. So I have, big memory. Oh, I'm already in that particular path. Normally it used to show here. So I can see the name of all the files that I have populated in that particular path. So I'm already in. Normally it shows me the folder name here. That's what was why I was confused a little bit. So now I am in that particular path. Now I would like to check the software availability using the module spider command that I was talking about. So I would like to have a list of files, softwares with this particular keyword. So I have to scroll. It's a long list. This is where R has been described. So these are the versions of R that has been installed on this HPC. So I can pick a specific version I would like to work with. This is the one I'm interested in. So I can load this module using module load command and then provide the name of the software. Now this version of R is loaded. So I can launch R, and this is the typical console you get when even you are working on your computer. So you should be able installing libraries or do whatever on the R console itself, or alternatively using the command that I showed you earlier to install packages. So if you would like to quit R and go back to the command line interface, you can use the quit command, and then you can say no to working workspace. Now you are back to the command line interface. So remember, to run a job using parallel computations, you need to have subfolders. So I have created a shell script that can automatically generate that for me. So this is a file name for the shell script that I'm using to create the subfolders that I was explaining, and then make symbolic links to all the important files that I would like to have symbolic link in the subfolder. So I have to run this shell script. There is an autofill option. If you are able to type part of the file, you can press the tab key on your keyboard, and it can autofill actually. And you can press enter. Now it's executing the job, meaning that it's creating subfolders and symbolic links automatically. So it makes life easy for us rather than creating subfolders ourselves and making or copying files manually. So this is a very handy way of doing the job. For some reason, it's quite slow. Normally, it's supposed to run very fast. So let me see if the subfolders are being generated. I don't see them here. Actually, this is a different HPC. So I have to go to CDAR, to the CDAR cluster. Yeah. Let me see if the files have been, the subfolders have been generated. It's quite busy. Yeah, the subfolders are created. And if we open any one of them, we can see the symbolic links. As you can see, the file size is quite small. So without having to risk the exceedance of your disk quota, you can have such a small files in the subfolders and make a symbolic link to the original file in the root directory. So now I have the subfolders and the symbolic links created. I have already created the R script for this job. I would like to test. I would like to test if this is going to work. If this is going to work, there is one aspect that I'm going to check before running the source code. Yeah. Now let me go back and this is the shell script I have prepared to test run, which is actually loading the version of R I would like to have or work with, and then calling the R script. So there are specific parameters. I use the salloc command, and then I have to provide the number of nodes I would like to work with, and then the number of tasks per node, which is 16 in my case, and then the memory that is required, it's 8 GB in my particular case, and then the maximum time for which the test job is supposed to run, 0 days hyphen, and then 00 hours colon 30 minutes. I would like to have a 30-minute maximum time for the job to run, and then 00 seconds. And then I have to provide which account I'm going to use is equal to, this is the account I'm going to use. And then for this particular job, I'm going to use additional argument that you normally don't do, because Alex has provided us with a specific reservation for priority purposes. So I have to include this argument as well. So it's research underscore demo. And then I have to type the name of the shell script. Yeah, then enter. I think it's returning an error. I have to check regarding what's wrong. Account, okay. There is a type error. We have to be careful with that. So I was supposed to use "C", not "O". And I'm still getting an error. Account, okay. There is still another error with account name. So, Cordero. Here we go. Now, it has granted allocation, and I'm getting an error. I will have to check what's going on by refreshing this. Actually, I'm getting an error quite early. I have to check library for each 4.2.1. There is no package called for each. Strange. I was not supposed to get this error. I have been testing it. Let me have a look. For each library, okay. And I'm using 4.2.1. Okay, 1 second. I can go to the home directory just to quickly check. This is R version that I'm using. So for each should be here. Yeah, the for each library is here. For some reason it's complaining, and I have been running this without any problem. Let me try it again. I'm getting the same error. I'm sorry. Maybe I will use a backup option that I have prepared with the local HPC. I don't need to go through the series of steps that I demonstrated. I would like to go straight to the Grex HPC, which is a local HPC system of the University of Manitoba. So let me log in. Normally it's supposed to run without any problem. So I have the session saved here, so I can open it. I provide my username and then my password. I'm in. So let me make change of directory to my working directory. And so now I'm in the right directory. I was submitting the job. So I have to start with providing the number of nodes, which is equal to 1. And then I can provide the number of tasks per node is equal to 16. And then I have to specify the memory, which is equal to 8 GB. And then I have to specify the maximum time, which is equal to 0 days, 00 hours, 30 minutes, and 00 seconds. And then I have to provide the account, which is equal to, I have to use double hyphen every time I define a parameter. So Cordero account is equal to, and then I have to type the name of the shell script that I'm using to submit. I am using to submit the temporary job. I've tested this, maybe it's complaining because of the number of nodes. It was working when I used 8. Tasks per node is equal to 8. So yeah, it's pending for resource allocation. So this is a backup. I'm sorry, I'm taking more time than I was supposed to. So now it's pending for the resource allocation. Depending on the availability of the resource, the scheduler will might take some time to allocate the required resource. The procedure is this, and once the job starts running, we can have a look at the output. Intentionally, I've introduced an error just for demonstration purpose, because I've changed the file name that was not supposed to have X as a suffix. So I'm going to get the same error that I was showing in one of the slides. Then we can include that additional argument to get more information regarding where the error is originating from, and we fix it. And then the goal was to submit a job. The job is still waiting for the resource. So rather than spending time here, I would prefer to go back and make an explanation of some of the output files that I have generated to, not inside here, but okay, let me go back to the home directory and then fbatch. And this is a particular folder where I'm working in. So I have prepared a backup R output files to show the error report. For instance, this is the error report that you get when you don't include that additional argument. So it gives you a crude information. It just cannot open the connection. It even doesn't tell what the connection is. So you have to be able to trace back to the origin of the error. This is the other option, the R output file, whereby the additional argument has been included to get more information regarding the error. So you'll get the same error. So it starts by spitting the same error that we saw before. On top of that, it tells where the error is exactly coming from. So it's telling me this file is missing. So I can fix this by removing the suffix that I have introduced. And then I can start submitting the job. So let me demonstrate how we can submit a job. I have to use the sbatch command and then provide the name of the submission script that I have prepared. This is the one I use. So it's the one that I was explaining. So it's basically loading R, defining the parameters, and then calling this R script. Now, this is the submission script. So now we have got a job ID, meaning that the job has been submitted. I can check the status by using the SQ command and then -u space my username. And then it gives me the list of all the jobs that I have submitted. This time it's just one. So normally it provides all the list of the jobs that are either running or pending. So the job ID, and then the name of the job that I was telling you to use to distinguish between the different jobs. And then the status, PD, means it's pending. The job has not started running. And if I would like to get more detail regarding this specific job, control show job, and then I can enter the job ID of my interest. So I get much more detail. So particularly, I'm usually interested in when the job is going to start. So I know the estimated time when the job is going to start. For some reason, if I have many jobs and I would like to know which particular script I use to submit or which working directory it is in, I can have a look at all of this. I'm sorry, with the Grex HPC still it's waiting in the queue, so I'm not able to demonstrate. I'm sorry for the technical difficulties. So this is the end of my presentation. And I would like to thank everyone for the attention. And if you have questions, you are welcome, please.
Okay, Ricardo, thank you for the demonstration. And this is one, I alluded to this at the beginning, right? Those types of errors also can occur. That's why you have a backup plan and the demonstration. I think we can still keep monitoring that job to see if it will run, to show the output. But in interest of time, maybe you can open the floor for questions. I don't know, Alex.
Sure. I can go back and check. In the meantime, maybe we can use our time for question and answer.
Sure.
So there's a question in Q&A session, which is different from chat. I'm not sure if you can see Q&A, if it's accessible on your side. If not, let me just paste it into the chat, and then I'll read the question. So the question is slide 15 and 16. Where are you adding these arguments? Are these part of your model parameterization script?
Slide 15 and 16.
Yes.
Okay. Let me go back. So slide 15 is this one. Full screen. These arguments, it's actually in the R script. It's in the R script. It's the R script where I'm creating clusters for the parallel computation. So this parallel library is a package of R, which I'm using make cluster command to create the different clusters on which I'm going to run parallel jobs. So it's inside the R script.
This is actually a very good point, because when you're working with HPC, you know, we have a particular workflow, right? It's all about developing a workflow using the piece of software that you choose. So for example, as Ricardo mentioned, he's using a small shell script that has the definition of the machine parameters, the HPC parameters, and then that script is calling R. And we use R here just to do the management of our model runs, right? The R will call the models, write the parameters of the models, because for this particular exercise, we're just running a few runs. But in the actual research, we run over a million model runs, right? So we have to use R to manage those calls. And then you have the hydrological model itself, which is called HYPE. I don't know if you picked that from the slides. So we have a string of software that's built within our workflow that for your particular application might be different. In our case, we developed it this way, right? Even the automation of folders that Bifekado mentioned, that was automated through a script. You could go manually and try to create the folders yourself, manually the way he showed. So it all goes back to the way you want to work. But I think one of the points that you want to make clear here for a beginner or a new user of HPC is start thinking about your workflow early on, right? Define how you want to run your application, how you want to solve your problem, especially if it's a big problem, how you are going to break it down. And going back to the question, like this error check is one thing that is really important for us, because when you manage hundreds of thousands of processes, you don't have time to be sieving through manually to see what it is. So that little output argument that Bifekado built into the R script, right? So this is within the R script. It's not in the shell command, in the bash file. So it helps us to identify when the code breaks, where is it breaking? And then you can go back and trace that and fix, right? Here he intentionally introduced one error in the error file to show you how it works. But the R script will break at that particular loop, and then you can go back and see, okay, that's the problem here. So I think that helps to, it's just the error checking thing that was important for us due to the sheer size of the exercise he was running.
Definitely. Thank you for the elaborated answer, Marcos.
Yeah, thanks, Bifekado.
It seems the job is running now with the error actually. So for some reason, it was not allowing me to successfully run because it was complaining about the library. Here it's running without any problem, as you can see here. So this is what I was planning to show. So rather than taking more time, I just would like to explain the nature of the job. So I have included the post-processing in the R script itself without having to wait until the job is completed. So it's running 112 calculations with 16 parallel processes, and then it's writing the stream flow in a matrix. And then the plan was to calculate the 95% confidence interval. So the post-processing step was also included in the R script, as you can see here. It's basically it starts, parallelizing the job here. The loop starts here and it completes here, and then the post-processing step is down below. So it's part of the R script without having to wait for the job to complete. One important aspect I would like to bring to your attention is the use of the big memory matrix. It's a package. The big memory is a package that allows you to save, to create a file-backed shared memory system, which can be treated as a computer memory when the computation is being done. So the fact that a matrix can be very fast compared to data frame when it comes to computation, this is a very good alternative. But the problem with matrix is you can have a problem with memory issue. This will help you to get around that problem without having to risk exceeding the memory capacity of the computer, because it's treating the file that has been saved as part of the memory for computation purposes. So you can use this for expediting your computation as well as avoiding getting errors of memory. And the other aspect is, typically in hydrological models, we get log files. So unless we make sure that we delete them on the fly, or unless there is some sort of turning it off. Usually they get printed, and depending on the model that you are running, the file can be the same and the information keeps adding and adding. Or sometimes, for instance, with Hype, you get different log files every time you run. So the number of log files can exceed your disk quota, and the job can be killed easily without you knowing what happened. So typically, I remove the job using this command. Go ahead.
This is quite important remarks you made, Ricardo, because for the memory allocation is one big thing, right? So for people out there, I know there's some people here that work with remote sensing. If you have those large data sets that do computation and keep those computations as floating points on the memory, you can have a memory overflow, and then your job might fail. So what this little trick that he's showing here with R, you write that information to a file so you don't risk losing your job because of memory overflow. So this is one thing. And the other thing is actually, managing the file size in terms of logs, because logs, they may grow really, fast, but they don't keep any useful information. So in this case, he's just managing the log files by deleting them as it goes. So we're managing, because this type of issue might cause your job to fail, especially if it's after several days. I know there's one question here on the chat, Ricardo. I'll let you address that. In the HPC, what's the difference between executing or running the same file in parallel and doing that through symbolic links?
Symbolic link is actually is different. I mean, symbolic link, the only thing that symbolic link does is we don't have to copy the file. We don't have to copy the file. We just have to make a kind of shortcut in the subfolder which points to the original file. So without having to move or copy big files, we can get access or read the files using just small size symbolic links. That's what it does. Running a job in parallel is something else, because we are executing, meaning that the symbolic links help us to be able to read the input files while the application is running. So every parallel process is running in individual subfolders, because it involves writing to the parameter file, writing to the output file. We would like to keep them separate to avoid interference. So when the job is running in parallel, the parallel computation for each process is using the symbolic link in its subfolder to point to the original file in the root folder. So they are separate things. I'm not sure if I have correctly understood the question, because symbolic link and running parallel jobs, they complement each other, but they are not the same thing.
Maybe I can chime in real quick. So Rodrigo, what happens is, for example, this is a scaled down version, right? So when you do, and Alex, please help me keep track of time, okay? If you run over time. But what you do is we have sometimes dozens, tens of folders, right, that you need to run our process from. If you were to copy all the input files and copy them in each individual folder, that would hugely increase the size of our exercise. So what you do is we only have one set of files and just have paths pointing to the same files in the root directory. So the models run, look at that root directory, look at the files, load them, and run. So you don't have to make several copies. So it doesn't influence the process. The process will still be parallel. It's just like the files that are being read by the process. Is it a single file or several copies of the same file in different folders? I hope this answers your question. So Alex, how are we for time?
We still have a few minutes. There's a new question in the Q&A. I'm just going to paste it into the chat. So the question is it possible to access sample scripts for this parallel process?
Yes, definitely. Definitely. In my workflow, I save all important files that I might want to refer later, because sometimes, depending on the nature of the job that you are running, you might get confused with which one is which. So usually I provide a very descriptive file name and then save all the necessary information along with the with all the samples I create. particularly to have
think
access to the script, the R script. He's talking about the R script that I have created, right?
probably. So I think they're asking whether they can have access to the script, where you can post it online, where they can download the script.
Definitely, I can put a sample script whereby people can use as a starting point to do their own job.
We'll coordinate that. We'll coordinate that with Alex, and I think Alex, you can post these slides as well, right? With maybe the sample script as well.
Right. Yeah. So the link that I just pasted. So this is the link to the schedule, and if you click on today's webinar, there it will take you to a page where we'll have the recording and all other materials. So the sample scripts will post there as well in that page.
Good. Maybe I should do a little bit of advertising here, Alex, as well, because the HPC group here also has a fall school, right? They have a series of courses. I don't know, Alex, if you have that webpage handy, but people have a series of webinars coming here from Grigory's team at U of M. They're preparing everything that you saw today in a specific webinars where they cover different levels of detail. So those are really great places to start looking at the resources and start looking at some of the aspects that Befecato talked about today. Is going to be covering much more detail there. So please have a look at those web page. Maybe I will send that to Alex as well to be circulated with the link for the video too. So
we'll do. Yep.
So can I give a very quick explanation about the output? This is typically what I was doing. I was calculating the 95% confidence interval. So based on the simulation that ran, I have the 95% interval for the parameter uncertainty as well as for the predictive uncertainty. So just based on the 112 simulations, normally I use much more sample than this. This is for demonstration purposes. So this is the output I get from the job. Thank you.
Yeah, thanks, Scott. Yeah, so we do all this. We go through all the pain of doing that to get this little graph, right? This is what we want. This is the result of our research. So this is what we're going to look at. And in the real case, how many simulations did you run, Befecato?
Depends, because I'm running many different experiments. Usually, I run for optimization purposes, I run up to 400,000 iterations. So that's quite a lot. And for sensitivity analysis, typically I use around 2,000 base sample size. So if I have, let's say, 40 parameters, 4,000 simulations that I was talking about was very realistic, actually.
Okay.
Very realistic. Sometimes, depending on the experiment I run, I increase the sample size to see how the sensitivity converges. And for a single research, actually, I have run up to 3 million simulations. And HPC is really very helpful in this regard, I would say.
Okay, there's another question here, Befecato. Is it possible to get the inline printing, like iteration number, for example, during the time, during runtime in real time while parallel computing?
Definitely. It's just the limitation of time that is not allowing me to explain everything. Typically, you might get frustrated, especially if you are running many simulations and you don't see any progress. When you open your R output file, it's stuck. You come back after one day, it's stuck there, and you might get frustrated. For that reason, I typically print when I print the index of my iteration. For instance, if I'm running from 1 to 1 million, let's say, I am parallelizing them. I'm parallelizing them using this. So over this iteration, I'm going to have as many parallel processes as the number of cores. I cannot print for individual process, but I can print over the loop, because when the index of the loop goes from 1 to 2, then I'm having 16 jobs completed in the first loop, 32 jobs being completed in the next loop. So I can keep track of where this percentage is. I can have a print to the R output file, because I'm using the RCMD batch command to submit the R script. It's going to generate an R output file with the same name as the R script. So I can just open that output file and have a look at the status, so that I know where the job is, at what point or the percentage, that's up to you. You can let it print to your output file so that you know where it is. Thank you very much for that important question.
Yeah, so as you can see, a lot of it is in the R script, right? So
yes.
Look, another question here before we go, last question. What's the reduction of processing time you can expect from HPC? You mentioned a 60-day processing time that was reduced to 30 days maybe, or 50, or maybe 50% faster. Can you speak to how much time you gain by using HPC?
It's roughly as let's say if I'm using 16 parallel processes, I can expect 16 times less approximately. Actually, it will be more than that because there is a communication cost between the parallel processes, and that can increase the timing a little bit, but roughly it can be as fast as the number of parallel processes that you are running.
Great, thanks, Pefecado. So I think we just went over to, I don't know, Alex, if you have time for any more questions, but people, please feel free. So one thing I missed is putting our contact info in the slideshow. But if you check that link that Alex sent, we have all the information that we need to contact us there, including the slide deck and some of the sample scripts that Pefecado worked through today. We can post some of them there. And hopefully this will help your journey towards HPC. If you have any questions, be willing to answer questions as well. Be communicate by email.